Okay, so we will start. Hello everyone, my name is Dong Zhang. Today I'm going to do my PhD defense. The title of my dissertation is Spatiotemporal Graphs for Object Segmentation and Human Pose Estimation in Videos. My advisor is Dr. Mubarak Shah. Spatiotemporal graphs are designed for the video-based problems, and they have nodes and edges which represent the spatial-temporal information in the videos. We have two types of spatial-temporal graph, type 1 and type 2. For type 1 spatial-temporal graph, the nodes represent entities in single frames. And let me give you one example. In this example, in frame 1, we have 3 entities. So we have 3 nodes here. And similarly, we have 3 nodes for frame 2, frame 3, and other frames. These nodes can be object proposals, pixels, superpixels, or the object locations in the video frames. And the edges, we can build edges between the nodes which represent color similarity between the object proposals, or distances between the moving objects, or the shape similarities between the segments in the video frames. For type 2 spatial temporal graph, the nodes represent entities in multiple video frames. Let me give you another example. In this example, the nodes can be object proposal tracklets, supervoxels in multiple video frames, and similarly we can build edges between this node, and the edges can be appearance similarities between the object proposal tracklets, or the motion models for the foreground moving object, or the overlaps between the superpixels. And in my dissertation, I have invested 3 important computer vision problems. And here, let me give you some examples for the spatial temporal graphs in these problems. The first problem, which can be solved by spatial temporal graph, is video object segmentation problem. In this problem, given a video, we want to get the pixel level segmentation for the foreground moving object. And let me show you the spatial temporal graph for this problem. We have a source node and a sink node. And for each of the video frame, we have some nodes to represent the object proposals. Basically, object proposals means the candidate region for the foreground moving object. And similarly, we have proposals for all the other video frames. And we can build edges between these nodes, which represent the similarities between the object proposals. And what we want to do is to select one object proposal for each of the video frame, and to make sure that they have the high objectness score and high similarity scores across the video frames. The second problem, which can be solved by spatial temporal graph, is the video object co-segmentation problem. In this problem, we have multiple videos as the input, and we want to segment all the objects from these videos simultaneously, and also we want to label the same object class as the same label in these videos. Here is one example of the spatial temporal graph employed by the video object segmentation problem. In this example, we have 2 videos, and we have the object proposal tracklets from these videos, and the nodes represent the object proposal tracklets, and the edges represent the similarities between the object proposal tracklets. And the goal is to select the maximum clicks from this graph, and each click corresponds to one object class. So after this process, we can get all the foreground objects from these videos simultaneously. The third problem, which can be solved by spatial temporal graph, is called human pose estimation in videos. In this problem, given a video, we want to estimate the joint locations. And in the results, I'm showing the different body parts with different colors here. Actually, we can employ different spatial temporal graphs to solve this problem. Here, I'm only showing one of the graphs I'm using in the proposed method. In this graph, each node represents one body part tracklets, tracklet throughout the video frames. And for each of the body part, we have multiple tracklets here. And the goal is to select one body part tracklet for each of the body part and to make sure that they satisfy the spatial-temporal relationship between these body parts across different video frames. Here's the outline of the rest of my presentation. As I mentioned, I investigated 3 important computer vision problems, so I'm going to introduce these 3 problems one by one. The first problem is the video object segmentation problem, and this work was published in CVPR 2013 as an oral paper. This problem has a lot of applications. The first application is the object recognition. If we can segment the foreground object from the background, we can build better models to detect the object. And the second application can be activity recognition. If we can segment the person from the background, it's easier for us to infer which activity it is. And the third application could be surveillance. If we can segment the vehicles from the background, we can track them more efficiently. This is a very challenging problem. The first challenge is due to the camera movement. As you can see from these 2 videos, not only the foreground is moving, but the camera is also moving. So it's very difficult to infer actually which region is the foreground region. And the second challenge is that we have to handle different types of object classes, and which means that we cannot just simply build a model for a specific object class. And the third challenge is due to the deformation of the objects. As you can see, especially for the animals or the people, they have different body parts, so it's very difficult to capture the body parts and segment them accurately. Here is the framework for the proposed method. We first generate the object proposals from different video frames. Then we build the spatial temporal graph using these object proposals in order to select the best object proposals from each video frame. And finally, we build the Gaussian mixture models for the background and foreground regions, and then use the Markov random field to optimize it in order to get the pixel level segmentation. The object proposal method can generate some candidate regions for the foreground moving object. In this example, in this video frame, we can generate so many object proposals, and we can assign an objectness score for each of the object proposals here. And let's examine some of the object proposals from the monkey dog video sequence in the SecTrack dataset. This frame is the 18th frame from the video, and as you can see, the third object proposal corresponds to the foreground moving object. And let's see frame 30. Also, the third the third object proposal corresponds to the foreground moving object. But this is not the case for the other video frames. For example, for frame 40, the first one, and for frame 51, the 17th one, and for frame 60, the 21st one correspond to the foreground moving object. So by this observation, we get the conclusion that the object proposals are quite noisy. So what we can do is to sample a lot of object proposals and select the right ones for each of the video frames. Let's look at another example. This is a parachute video from the SecTrack dataset. And if you look at these object proposals carefully, you will find that none of the object proposals corresponds to the complete foreground moving object. And by this example, we conclude that we have to combine multiple object proposals in order to get the complete segmentation for the foreground moving object. Then after we got the object proposals from each video frames, we build the spatial temporal graphs using them, and in order to get the best object selections from each video frame. In the graph, we have nodes and edges. Actually, we have 2 types of edges, the unary edges and the binary edges. We use 2 nodes to represent one object proposal, a beginning node and an ending node. And we build a unary edge between them to represent the object needs. And for the unary score, we're using the combination of the motion score with the appearance score. The motion score, we use the average Frobenius norm for optical flow gradients, which has this equation. And for the appearance score, we're using the score from the object proposal methods. And here is the illustration for the how we get the motion score. For one video frame, we calculate the optical flow here, and this is the object region, and this is the optical flow gradients. As you can see, the optical flow gradients have higher values around the boundary of the object region. That's why we get the boundary region of the object proposal, and then we use the optical flow gradients around the boundaries to compute the motion score. For the binary edges, we build them between the nodes in adjacent video frames, and actually the nodes are fully connected for the adjacent video frames. And also we have a type of edges which connect the, say, frame I to frame I plus 2. We design these kind of edges because we want to handle occlusions, because for frame I plus 1, the object might be occluded by some other objects, or in this frame we just cannot get good object proposals. So we have to jump the object proposals to the next frame in order to select the good proposals. And for the binary edge score, we're using a combination of the overlap score with the color score. So for the overlap score, we're using the intersection over union between the two object proposals. And for the color score, we use the dot product of the color histograms between these two object proposals. And this is the final spatial temporal graph to solve this problem. We are not showing all the edges here for simplicity. And our goal is to find only one object proposal from each frame, such that all of them have high objectness score and high similarity scores across the video frames. How to solve this problem? Actually, we can add two nodes to the graph, a source node and a sink node. And then this problem becomes to find the longest weighted path in the DAG. DAG represents the directed acyclic graph. And actually this is a typical problem for the DAG, which is called longest path problem. And it can be solved efficiently by dynamic programming. Here is the dynamic programming formulation for the problem. We have the objective function, which basically means that we want to get the longest path from this graph. And in this equation, E means the scores, which can be the unary score or the binary score. And Pi plus 1 represents the nodes in the graph. For the dynamic programming, we have to find the recurrence function. And in the recurrence function, OPT ij means the optimal solution for ith node in jth frame. So basically, this recurrence function means that for a specific frame, we loop through the nodes in this frame and get optimal solution for each of the node. And then we proceed to the next video frame. Finally, we build the Gaussian mixture models for the background and foreground regions. And for the GMMs, we are using two features, the color feature and the location feature. And then we build a 3D graph for all the pixels in the video frames. And we use Markov random field to optimize this graph in order to get the pixel level segmentation like this. And for the MRF, it has unary terms and binary potentials. And for the unary potential, we are using the output from the GMMs. And for the binary potential, we are using the color similarities between the adjacent pixels in the video frames. Let me show you some results from the SecTrack dataset. This is the growth sequence from the SecTrack dataset. I'm showing the original video on the top left and the ground truth on the top right. And on the bottom left, I'm showing the selected object proposals by the proposed spatial temporal graph. As you can see, For some of the video frames, the proposals look very nice, but some of the other proposals, the segmentations are not complete. And on the bottom right, I'm showing the final segmentation after the Markov random field. As you can see, the results looks much better and more consistent throughout the video frames. Here's another results from the parachute video in the same data set. And it's very clear that for the selected object proposals, especially for the last few frames, the proposals do not look very good. And after the final optimization, we get very accurate segmentations for the parachute in the video. Similarly, here I'm showing the bird fall video from the same data set. And this is the cheetah video from the same data set. This video is extremely challenging because the foreground object looks very similar to the background, but still we can get good segmentations for the object. And here I'm showing another long video sequence, which is the monkey dog video sequence. This video is challenging because the monkey actually is a deformable moving object. It has different body parts which moves very fast, but still we can capture these body parts accurately and get good segmentation results. Let me show you some quantitative results on the SegTrack dataset here. I'm comparing with 4 of the state-of-the-art methods here, and 2 of them actually are using some of the ground truth segmentations to guide the segmentations for the rest of the video frames. And actually 3 of the methods are not using any of the ground truth segmentation, so we call them fully automatic method, including our method. And for the numbers, I'm showing the per pixel error rate. So the smaller the better. For example, for the bird fall sequence, our error is only 155, but for the second best method, it only gets 189. So similarly, we get better results in other video sequences also, and by average, our performance is 452, but the best of the state-of-the-art methods only performs 542. Our method performs much better. And in summary, we have demonstrated that spatiotemporal graphs can be employed to extract the foreground moving object from the video. And also it can help the pixel level segmentation. And we have demonstrated that we improved the results for more than 20% on the publicly available data set. As you might see, video object segmentation only handles single video. So can we use multiple videos to improve the segmentation? And to answer this question, I will introduce the second problem, which is the video object co-segmentation problem. We have published this work on ECCV 2014. Also, this problem has a lot of applications. First, for automatic annotation. In this example, I'm showing 2 images, one training image and one testing image. And for the training image, we have the segmentation annotation, but we don't have it for the testing image. What we can do is to do the co-segmentation for the training and the testing images. Then we can propagate the annotations to the testing image also. The second application could be unsupervised object detection and recognition. In this application, we don't need the bounding box annotations for the objects. We just simply do the co-segmentation for these images or videos. Then we will have a very fine level segmentation for the object. Then we can build the object detector using these segments. The third application could be human re-identification. For the traditional methods, they extract multiple features to identify a person from different video frames. But by using the co-segmentation, we can just simply do the co-segmentation for all of these video sequences, and the same person will be identified from different videos automatically. It's also a very challenging problem. First, because the appearance variation. As you can see, in the same object appears very differently in different images or videos. They have different colors or different shapes. And also we need to handle different multiple object classes. And third, it has a much higher complexity compared to the video object segmentation problem, because the complexity actually increases exponentially with respect to the number of videos. Here's the framework for the proposed method. We first generate the object proposal tracklist from all these videos. Then we formulate the problem into a regulated maximum weight click problem for the tracklist, and solve it by a modified version of the Brown-Kirbosch algorithm. And finally, we build Gaussian mixture models for the objects and use the Markov random field to get the final pixel level object co-segmentation results. This is the first stage. We generate the object proposal tracklists. These are some video frames, and for each of the video frame, we can get multiple object proposals, and we track these object proposals backward and forward using this similarity function. And after this step, we will have a lot of object proposal tracklists in every video frames. And we will use these object proposal tracklists in the next stage, which is called regulated maximum weight clicks for the tracklists. Let me show you one example to demonstrate the proposed algorithm. In this example, we have two videos. In video 1, we have a chicken and a turtle inside, but for video 2, we only have chicken. So as I mentioned before, we can generate the object proposal tracklist for both of the videos. And for video 1, there are some tracklists for the chicken, some tracklist for the turtle, and also there are some noisy background tracklists here also. And for the video 2, we have the tracklist for the chicken and background. And we use the nodes to represent these tracklists. And for each of the node, we assign a weight to it. Basically, the weight is the sum of the objectness weights within this tracklist. And what we want to do is to find the regulated maximum weight clicks from this graph, and we're using a modified Brown-Kirbosch algorithm to solve this problem. After applying this algorithm, we will find some clicks like this one. This is the largest click from this graph, which consists of 6 nodes. 3 blue nodes are from the left video, and the 3 green nodes are from the right video. And all of these nodes are the chicken tracklists. And similarly, we have a smaller click here, which consists only 3 nodes, and all of these 3 nodes are from the left video, which correspond to the turtle tracklists. And we're going to use these clicks to get the video object co-segmentation results. And here's the algorithm. We have the objective function for the regulated maximum click, which for WC is the combination of a constraint term and the sum of the objectness term. So for the objectness term, it's just the sum of all the objectness scores for the object proposals within a click. And for the constraint term, it's the color histogram normalized by the number of combinations of the color histograms. And for the algorithm, we first apply the Brown-Kirbosch algorithm to find all the maximum clicks from the graph. And then we calculate the weights using the previous objective function. And then we select the largest click from the graph, which corresponds to the first object class. And then we remove this click from the graph and select the next one iteratively. By this, we can get multiple object classes from these videos automatically. Let me show you some results here also from the movie CS dataset. This is the chicken and the turtle video sequence. I'm showing the original videos on the left side, and on the right side I'm showing the co-segmentation results. I'm using red to represent the chicken, and turtle I'm using the green. So you can see we not only can segment the objects from the background very accurately, but also we can get the labels correctly. And here is the elephant and the giraffe videos from the same data set. In the first video, we have a giraffe, and in the second video, we have both elephant and the giraffe. You can see that we can get quite good segmentations for the objects also, although there are some mistakes in the first video. And the third video set is called the lion and zebra video set. This video set consists of 4 videos. And in the fourth video, we only have zebras, but for the rest of the 3 videos, we have both zebra and lions. And for most of the videos, we can segment the foreground object clearly from the background, and also give them the correct labels. Let me show you some quantitative results on the moving CS dataset here. I'm showing 2 versions of the proposed method. Ours 1 means that we are using same parameters for all the video sets. And for ours 2, we fine-tune the parameters for different video sets in order to get better performance. And we compare our method with 2 of the state-of-the-art methods. And for the numbers, I'm showing the intersection over union metric, which means that the larger the better. For example, for the chicken and the turtle video set, our performance is 86%, but for the second best method, the performance is only 65%. And this is the same for all the other video sets. And overall, our performance is around 58%, but the best of the state-of-the-art method only performs 49%. In summary, in Chapter 1, we have demonstrated that Type 1 spatial temporal graph can be employed to solve the video object segmentation problem. And in Chapter 2, we have shown that Type 2 spatial temporal graph can be used to solve the video object co-segmentation problem. And for both of the problems, we have improved the results dramatically over the state-of-the-art methods. And for the video object segmentation and co-segmentation problems, we handle generic object classes. So what is the most important object class in the videos? As we know, it is human. So this brings us to the third chapter of my dissertation, which is human pose estimation in videos. And we have published this work in ICCV 2015, and an extension of the work was submitted to PAMI. Let's see one example for the human segmentation results by using the video object segmentation method I just introduced. As you can see, for some of the body parts, we cannot get very good segmentations, and actually these body parts are missing. And the human pose estimation method can identify the locations of the body parts. So what we believe is that by using this fine level information, we can improve the object segmentation results. The human pose estimation has a lot of applications, and the first application is the action recognition. In videos, if we can identify the body part locations, it's easier for us to identify which action it is. And the second application is the HCI, human-computer interaction. And this is extremely important for the video games. And as you know, Microsoft Kinect is doing similar things, but actually they are using different sensors. And the third application could be the surveillance. If we can estimate the human poses for all the people in the video sequence, we can track them more efficiently and accurately. It's an extremely challenging problem, mostly due to the huge appearance variations for the people inside the video, because people are wearing different clothes, and also they have different gestures, so it's very difficult to localize correctly where are the body parts. And also we need to handle multiple people. If there are multiple people inside the videos, there might be some occlusions between the body parts or confusions between the body parts. And also we want to get consistent estimations for the human poses. It is true that we can simply apply the image-based human pose estimation method to each of the video frame, but that will make the results very noisy. So what we want to do is to use the temporal information in order to get a consistent pose estimation throughout the video frames. Here is the framework for the proposed method. First, we generate the human pose hypothesis. Body part locations, and the edges. For the yellow edges, these are the spatial constraints between the adjacent body parts. These type of edges are commonly used by the researchers. And there's another important edges, which are the blue edges. These edges model the symmetric nature of the body parts, and these type of edges are not used very often by the researchers because it will make the problem more difficult to solve. And since we are handling videos, we have to build another type of edges, which are the red edges. These edges model the temporal information, which means that we want to make the body part estimation consistent throughout the video frames. And as you might see, there are a lot of simple cycles in this graph. One type of the simple cycle is called interframe simple cycles, which means that this simple cycle is within one video frame. And another simple cycle, we call this type of simple cycles the interframe simple cycles, which means that these kind of simple cycles are across video frames. As you can see, there are too many simple cycles in this graph, which makes the problem NP hard. So what we want to do is to remove these simple cycles without satisfying the performance. We have two ideas to solve this problem. The first idea is called abstraction, and we use this idea to remove the interframe simple cycles. And this is the original body part relational graph. And since in this graph we are using different nodes to represent different body parts, we call this graph real body part relational graph. And what we did is to combine the symmetric body parts together. For example, for the left and the right foot, we combine them together to be one single node, which is called the feet node. And then we will have a new graph. And this new graph has a tree structure. The inference problem for this tree structure can be solved very efficiently by dynamic programming. And since in this graph, the nodes actually only has some abstract concept for the body parts, we call this new graph the abstract body part relational graph. The second idea, we call it association. By this idea, we remove the interframe simple cycles. Since we already have the real body part, abstract body parts definitions, it's easier to understand this idea. Basically, we just track these abstract body parts throughout the video frames. Then we will have the final graph. We call it a post-relational graph. In this graph, each node represents one body part tracklets. So that's why we also call this graph the tracklet graph. Let me show you different stages of the proposed method. In the first stage, we generate many full body pose hypotheses for each of the video frame. Like this, the yellow one, the green one, the red ones. They are the full body pose hypothesis in this video frame. And in the second stage, we generate the real body part hypothesis for each of the video frame, which basically means the body part locations, the candidate body part locations in this video frame. And we do it for all the video frames. Next, we are going to combine the left and the right, the symmetric body parts together to be one body part. In this example, we combine the left and right feet together to be one feet. And by this stage, we convert the real body part relational graph to the abstract body part relational graph, which simplifies the problem. And then we want to track these body parts throughout the video frames using this tracklet hypothesis graph. And after this stage, we will have the tracklets for different body parts. For example, the red tracklets are for the head, and we have the green tracklets for the feet. And actually, this graph is very similar to the video object segmentation graph I introduced just now. And in this graph, each node represents one body part locations in the video frames, and the edges model the similarities between the body part locations in different video frames. And what we did is to get one tracklet from this graph and then remove the related nodes for this tracklet. Then we do this again multiple times in order to get multiple tracklets from the graph. Similarly, for the graph, we have the unary weights for the nodes and binary weights for the edges. The unary weights actually is the combination of the detection score with the foreground score. Phi m here is the detection score we obtained from the n-best method, and phi f is the foreground score we got from the background subtraction algorithm. And we have the binary weights, which is the combination of the chi-square distances between the two body part locations and the distances between the two body part locations in different video frames. And finally, we have the objective function, which is the combination of the unary weights and the binary weights. And since we have this objective function and we have the similar graph to the video object segmentation problem, we can solve this problem efficiently using dynamic programming. And as the last stage of the proposed method, we call it tree-based pose estimation because the relational graph for this problem is a tree. And this is the pose hypothesis graph. And in this graph, each node represents one body part tracklets throughout the video frames. And for different body parts, we have multiple nodes to represent multiple tracklets. And the goal is to select one body part tracklet for each of the body part and to make sure that they satisfy the spatial temporal constraints for the body parts within a single frame and also across the video frames. And after this stage, we will get the final human pose estimation results from all the video sequences together. Let me show you some quantitative results on the outdoor data set first. This is a video from the warm-up video in this data set. And we compare our method with the n-best method. N-best method is the best of the state-of-the-art method. And as you can see, our estimations are very consistent throughout the video frames, and the n-best method are not very consistent, and the body part locations jumps everywhere. And here I'm showing another video sequence, the bounce video sequence from the same data set. And still our method performs better. And the n-best method has another problem, which is called the double counting problem, which means that the left and right body parts are detected at the same location, especially for the legs. And here I'm showing the results from another two video sequences from the outdoor data set. And similarly, our performance is much better and more consistent throughout the video frames. And we did experiments on two other data sets also. The n-best data set, which contains two videos, and there are a lot of body part occlusions. And this is the results from Walk Street video from the n-best data set. And since the legs are occluded in multiple video frames, our method performs better than the unbest method also. We also did experiments on the human EVA dataset. This dataset is an indoor dataset, so they have very good annotations. But for unbest method, you can see it cannot even identify the person in some of the video frames. But for our method, our estimations are quite consistent, and we can always localize the body parts and the person in the video frames. And similarly, we have the results for another video sequence from the human EVA dataset. Then let me show you some quantitative results on the 3 datasets. Here I'm showing 2 evaluation metrics, the PCP and KLE. The PCP is a precision metric, so the larger the better, but for KLE it's an error metric, so the smaller the better. We compare our method with 2 of the state-of-the-art methods, and as you can see, the best of the state-of-the-art method performs only 86% for the PCP metric, and by average our performance is 92, so it improved a lot. And similarly for KLE, the improvements are even more. We reduced the error for almost 50%. And for human EVA dataset, similarly we have improvement by using the PCP measure, and also for KLE, the improvement is more than 50% by average. And for the unbest method, the second best method only get 80% of accuracy, but our method by average it can get 91% of accuracy here. And for the KLE, the improvement is even more. And in summary, in chapter 3, we have demonstrated that human pose estimation can be well formulated into spatiotemporal graphs, and the graphs can be employed in different stages in the human pose estimation problem. And we have demonstrated improved results on publicly available data sets compared with the state-of-the-art methods. And in conclusion, we have explored the generic object segmentation in videos in chapter 1 and chapter 2. In chapter 1, we deal with single video with the video object segmentation problem. And in chapter 2, we're handling multiple videos, and we can segment the objects from all these videos simultaneously. And as the most important object class in the videos, human, we explored the human pose estimation problem in chapter 3. And in conclusion, we have shown that the spatial temporal graph can be applied to many computer vision problems. And for the 3 important problems we investigated, we have efficient and exact solutions. And we have found that dynamic programming is especially important to solve these problems. It's, for example, for the video object segmentation problem and the human pose estimation problem. We have shown improved results for all of these 3 problems. And for future work, for video object segmentation, we need better object proposal methods in order to get more accurate segmentation for the objects. And since the proposed method is not very good at occlusion handling, we need to improve that also. And for video object co-segmentation, since the same object appearance varies a lot across different videos, we need to design some robust object matching algorithms. And also, although our performance is already best, still the performance is only 60% on the movie CS dataset, so we need to improve the results a lot. And for the human pose estimation problem, what we found is that most of the method identify the joint locations by appearance information only. And what we believe is that the motion information can be very helpful for the joint detection also. And we need to handle multiple peoples. This is challenging because there might be a lot of occlusions or confusions between the body parts in the video frames. And since we have explored 3 important computer vision problems in my dissertation, and it's very encouraging for us to investigate some more problems like multiple object tracking or action recognition. And also for different problems, we need to design different graphs. We need to design the graph structures and also the solutions to make it efficient and produce better results. And to handle the real-world problems, we need real-world implementations for all of these algorithms I introduced. Here are some publications during my PhD study, and this is the end of my presentation. Thank you.
Okay, questions?
I have a question.
Yeah.
So, how extensible are your proposed solutions? So, for instance, we're talking about higher dimensions. If let's say we say let's say 4D ultrasound or those kinds of data sets. So, can these proposed solutions can be applied to those in higher dimensions?
Yeah, sure, definitely. I mean, it depends on the features, I think. Because basically, for example, for the video object segmentation method, we build a graph. It has unary term and a binary term. So based on your features, you can just assign the values to the unary and binary terms, but it will not increase the complexity. If you have some good features which can get useful information from your high-dimensional data set, I think the method can be used in your problem also. Yeah.
I have another question.
Yeah, sure.
So previously you were using two, like one was color information and the other was location information for computing.
Yeah, the binary edges. Yeah.
So can you incorporate also some kind of shape descriptors or for your video segmentation or for high dimensions?
Yeah, sure, definitely. I mean, shape is another kind of features, right? So for I think it's more important for the high-dimensional data. But for the 2D dimensional data, like the images, I mean, it might be helpful, but still, since the results are already good, I think it will not improve the performance that much. But for high-dimensional data, I agree, it's very important. Yeah.
Yeah.
When you're combining, when you're doing the pose estimation, you're combining 2 arms in 1 arm, right?
Yeah.
So aren't there many possible positions for 2 arms that result in 1 combined arm? Is there a unique mapping?
Let me see. Yeah, there's no there's unique maps between the encoding, because actually in our solution we don't remove the information for the 2 body part locations. We just encode them by a single node. But in this single node, it still has the information for the 2 arms. So it does not lose any information. It's just for the representation, we're using 1 node to encode the 2 arms. Yeah.
It's just abstraction. Okay, more questions? Any question from the audience?